Okay. So we have an exam a week from today. That's exam 1. Which is October 5th. And what I like to do before exams, first of all, you'll see that one of the handouts I gave out today, which is already posted on Blackboard, is a set of review problems. Some of them we're going to be getting to today. And what we do today will be on the exam. But what I like to do is I like to have some extra problem sessions with the students, with you guys. So we need to set some times that would be good where some of you would want to come to a problem session. So I threw out some times last time. I wonder if you had any time to think about that and come up with what's good for you. Yeah. Oh, I thought someone raised their hand. I was so excited. Sylvia, what about you? Well, I was suggesting we, of course, there's tomorrow, which nobody wants to do because it's so far before the exam. But it would be a great idea because then you still have the weekend. And I'm free most of the day tomorrow, except for between 12 and 1. And then there's Monday, where I'm pretty much free most of the time also. And then there's Tuesday. I suggested I could do after class, and I know some of you have lab, but then I could also do after lab. So, I mean, we could stay in this room from 12 to 1 on Tuesday, and I could also meet, say, 3:30 to 4:30 on Tuesday. I'm just suggesting these possible times. I'm also Wednesday, we could do it after 2. So what, I need, if you're not going to come, then, don't tell me a good time because, and also I offered to do a Zoom, which would be on Sunday from home. Any ideas, folks? Because I'm only going to spend 2 minutes on this and then we're going to move.
After class.
Okay, how many people would come then?
Tuesday, from 4 o'clock. I could come on Tuesday.
Oh, okay. 4 to 5.
Yeah.
I know some people have lab then as well, but that's all right. I mean, so I'm kind of interested in people who can't make these times, when could you folks come? Could you come Monday? What time?
Yeah, before 4.
So how about 2 to 3? What about you back there? Well, when can you make it? And what? Well, I'm not going to do it 6 to 8, but how about if I started at Monday? Monday morning, that's when I go swimming.
Self-care matters.
What time Monday morning?
After 10. That's early.
That's when I go swimming, 10. I could meet at like 9. Wait, I'm still working on these people back here. So what was your suggestion? Behind Juliana. Oh, this Friday? What time do you want? I can't do it between like 11:45 and 1:15. So like 1:30? Okay, that's good. Wait, I haven't done anything I'm not going to have like 10 of these, but I'm still interested in the people back there. What if I did Monday, like 3 to 4? Is that possible?
Actually,
Yeah.
we can do too as well.
Okay. All right. So, Friday at 1:30 being I'll sign up for the conference room in, building 2. Tuesday we'll meet here. Are these times on Tuesday good for you? Okay. After lab, maybe, well, but there's a lab in that room, so I can't teach it in the lab room. This will be right here. Monday 3 to 4 is probably gonna be, well, this is a lot, 4, that's enough. I'm not gonna do any more than that, I don't think. Monday 3 to 4, I'll sign up for the conference room, but I'll have to let you know, I'll post all this on Blackboard and I'll figure out where to have this as well. So, all right, are these times, yes? Sorry, when will it go to? I don't know, when do you want it to go to? You can make it if it's like wet, what? How does it impinge on your availability? Okay, I'll still be there at 2:30, so I'll put 3, but at least that. I could be there later. All right, so is everybody happy with these times? All right, then that I'll write it up and I'll put it on Blackboard. Now it's your turn to work. I would like you to do this problem. So this is a grams to moles to moles to grams. This is a typical problem in chemistry. I think that at the end of my high school course, at the whole year was over, that's what I learned how to do. That's it. Yeah. It was a rough year. Oh, by the way, I have office hours on Wednesday, 2 to 4. So you could just look for me there if you need me. Anyway, so this is a problem where you start out with a certain amount of a reactant, burns completely, simply means it undergoes this reaction, which is combustion. And it's asking what mass of oxygen reacts with that and what mass of carbon dioxide forms. And you've got to do this one step at a time, right? So you're going to start with the grams of the reactant. And you cannot go directly from grams of a reactant to grams of another reactant or grams of a product. What do you have to do? You have to convert it to moles. Right. How do you do that? What do you use to do that? Yes, use the molar mass of this compound, which is given, okay? Then you have moles of C2H6O2, but you don't want that, right? We're doing this first, the oxygen. So we want to get moles of oxygen from that. And how do you do that? What happens for this arrow? What's going to help you there? The mole or stoichiometric ratio, which has to do with the coefficients, okay? And then finally, we're going to convert the moles of O2 to the grams of O2, which again, you use the molar mass. So now, if you're me, or if you're, you're comfortable with it, you can do this one parentheses after another and do it all at once. Okay. Then you do the same thing, but you're trying to find out how much of the product CO2 forms. So the only thing that changes is that you'll be getting moles of CO2 here and then grams of CO2. Otherwise, it's very similar. So go. Talk to your friends if you don't know what you're doing. Talk to me. I'm going to come around. Hi. What? That's okay. No problem. Take this. You were here last time.
Yeah, I already got that.
This is the problem that's on the sheet of paper, so you don't have to look at it up here. Some people like it in front of them. It's the first problem. What are you doing? You're not doing anything. Oh, you did it already? Okay, wow. Boy, I'm impressed. Good. You did both of them?
Yeah.
All right. What can I give you to do in the meantime? I can do that, yeah. But what can I give you to do though? Because
Do the second one.
well, that one you don't know how to do yet. There was one we didn't do last time. I think 4B we didn't do. Activity 2, 4B, I don't think we did that. Why don't you do that? Yeah, I don't even have the answer to that. It's like same things. So 3. These are exact, all ratios are exact. Relatively.
And then above here. With that.
I haven't changed my thing yet.
Well,
I didn't get it.
Cool. Yeah.
We always felt it was like a little 10, 20.
Yeah, I think it's.
Obviously, you're doing it right, but something is going wrong. All right, all right, all right. So has anyone got a real burning question about this? I'm gonna go over them, but it's gonna be pretty fast. So you start just like with the 27.4 grams. And now I'm gonna follow my recipe here, and I'm gonna use the molar mass, which is given. Which you put in that way. A lot of people like to put grams per mole and then per mole, but that's not what it is, right? It's grams per 1 mole. So you write it this way. If you were to do the math here, you would end up with 0.441 moles of C2H6O2. But I don't want to stop here. Oh, I really have to do better with my labeling. And here is where I use that stoichiometric ratio, 5 moles of O2 per 2 moles of C2H6O2. So my moles of C2H6O2 cancels. I already canceled the gram. So now if I do the calculation here, what will I be calculating? What will my answer be? What will it refer to? Moles of O2, right? And it would come out to 1.10 moles of O2, but I don't want to stop there. I want to convert that to grams. So my moles of O2 cancels, and when I do the math here, it comes out to 35.3 grams of O2. I saw that a lot of people had that answer, so I was happy to see that. Okay, now let's do the other one. We start the same way. In fact, I do exactly the same thing at first. I could even use this number and start there, but I don't know, whatever. So now I have a different mole ratio, right? I have to look at the CO2 and there's a 4. So it's 4 moles of CO2 per 2 moles of C2H6O2. I've already gotten rid of grams of C2H6O2. Now I'm going to get rid of moles. If I do my calculation here, I will have 0.882 moles of CO2, but I don't want to stop there. I'm going to convert it to grams. And when I do this, I get 38.9 grams of CO2. I saw that number a lot too. So if you have a question, now is the time to ask it. All right. So, there's a million variations of these stoichiometry problems. And one of the very important variations that you need to learn is what happens, what to do if a reaction is in solution and you're given, instead of the number of grams of something, you're given the molarity, the concentration, the molarity of a reactant, let's say, and its volume. Okay. So we can do stoichiometry problems starting with this type of information as well. So instead of starting with grams and converting grams to moles, so before we did grams to moles, now we're going to do molarity and volume and convert that to moles. But we know how to do that, right? Because molarity, if you remember, is moles per liter. Okay, so molarity is moles per liter. So the number of liters times the molarity gives you the moles. And so we know how to get moles that way as well. And there are other aspects of this problem as well. Instead of, say, getting grams of product, you may be asked to get the concentration of a solution at the end, concentration of a product at the end of the reaction, something like that. So let's do this problem. 250 milliliters. This is the second problem on that sheet. 250 mLs of a 5.00 molar solution of hydrochloric acid, that's HCl, reacts with zinc metal in this reaction. This is a reaction we're going to study next week. It's called a metal, I call it anyway, a metal plus acid reaction. And you end up with hydrogen gas and an ionic compound that's formed from the ion of the metal and the chloride here, in this case from the acid. But the mechanics of, how this reaction, what it is and what products you get is something we're going to study next week. But what's asking here is how many moles of the product zinc chloride are produced? And what is the concentration of that zinc chloride? Because notice it's aqueous, so that means it's dissolved. So the question is, what is the concentration in the solution at the end of the reaction? So here we have a situation where you simply have a flask in which you have 250 milliliters of the HCl solution. Okay, and we know what the concentration is. And then, you just take a piece of zinc and you just put it in there. That's the zinc being added. So the volume at the end is really the same as the volume at the beginning. That zinc is actually going to disappear. There's no zinc at the end of the reaction here. It's all dissolved salt, dissolved substance, and H2 gas, which bubbles away. So the whole volume at the end is 250. So that's kind of the scenario of what's happening in this reaction. But what's different here is now we have to figure out, here's what we're given. Remember, start with what you know. And what you know is the concentration and the molarity of the HCl. So what you need to do is get the moles. And how we're going to do that is we're going to multiply the volume in liters by the molarity. So 250 milliliters is 0.250 liters. Now I would move the decimal place 3 places. If you want, you can do it this way. But we do this so often in this class that I hope that you will get used to just moving the decimal point 3 places. And then we'll take that 0.250 liters, and I like to write it like this. I like to write my molarity in a parentheses, because then I could do it this way. I can say molarity is moles per liter, and then my liters will cancel, right? So that tells me that I'm multiplying by the 5, not dividing by it, because I would get the wrong units. Okay, when you do that, you get 1.25 moles of HCl. And now it's just the same as ever to go from the moles of HCl to the moles of ZnCl2. Oh, but one thing, what didn't I do in this reaction? I did not balance it, and you have to balance it. So I guess I would say that you must use a balanced equation. So I'm going to balance it now. So all I had to do is put a 2 there. Now I have 2 Cl's on the left. I have 2 Cl's on the right. I have 2 H's on the left. I have 2 H's on the right, and I have 1 zinc on each side. So it's balanced. So I could take my 1.25 moles of HCl, and I have 1 mole of ZnCl2 per 2 moles of HCl. And since I don't have enough room, I'm gonna just calculate these moles, slightly different here. And you get 0.625 moles ZnCl2. So our first step, I guess I should write this down maybe. First step was to get the moles of HCl. from the molarity and the volume in liters, and that's what I did here. Now, then the second step is to use the mole ratio of zinc chloride, the thing we want to get, to HCl, and I did that here. And now finally, what's the third step going to be? Because what are you asked to do? Okay, we have the moles. That's A, we did A. Now for B, what do I have to do here? Yes. That's right. And the number of liters hasn't changed. It's still the 250 milliliters. So I have to divide my moles of ZnCl2 by volume in liters, which is still 250 milliliters. So it's 0.625 moles over 0.250 liters equals 2.5 molar ZnCl2. So that is the concentration of the zinc chloride in the product. Yes. Well, okay, you dump in a piece of zinc metal. That might bring the volume up a little, but then the zinc reacts away and it forms dissolved zinc chloride and the volume will go back down. Also H2 gas, which is coming out. It's just bubbles and it goes into the air. You know, even if it changed a little, in Gen Chem, we're not going to account for that type of thing in these types of problems. So there are examples, and I think I have one in here, where you take two solutions and mix them together, right? And then, of course, you have a different volume at the end than you had at the beginning, and you would have to divide by the total volume. So there are cases where you would have to do that. Okay, so let's move on to the next solution stoichiometry problem, this one here. And again, you're given the volume and the molarity of a reactant. Oh, let's balance this equation first. So how do you balance this one? Where's a glaring mistake? Something that's got 2 on one side and something, yes. Yeah, there's 2 NO3s here, and there's only 1 here. So you're going to put a 2 there. Okay. But now that means you have 2 silvers as well, so you have to put a 2 here. Yes. Because molarity is defined as moles per liter. Yeah. So if you do this, you could see that you have 2 silvers on each side. You have 2 nitrates from here. You have 1 magnesium. And you have 2 CLs. Because you have 2 there and 2 there. So this is balanced, done. Okay, so now we're given a volume and a molarity of one of the reactants, and it says it reacts completely with a 25 milliliter solution of MgCl2. Notice the concentration of the MgCl2. How do I know the MgCl2 is dissolved? How do I know it's dissolved and not solid? That's right. And also it says aqueous in the equation. That's correct. So both of these are dissolved. So I start with a solution of this and a solution of this, and I add them to each other. So the final volume of this solution is going to be different at the end. Like, remember the last example, we just added the zinc, it disappears, the volume doesn't change. Here we're adding 50 mils to 25 mils. But we don't know the concentration of the MgCl2. That's what we're trying to find out, is how much product is produced. So we're just going to use the amount, use the molarity and volume of the AgNO3 to get moles of AgNO3. And then what is the second step going to be? So this is my strategy. What's the second step? Once I have the moles of AgNO3, what am I looking for in this problem? You see that? I'm looking for the amount of magnesium nitrate. That's a product. So I'm gonna use the moles of AgNO3 to get what? Just say it. Yeah, NO3 too. Okay, and now, but what's being asked here is, what is the concentration of that MgNO3 in the final solution? That means what is the molarity? Okay. So how do I get that? What's molarity? Sometimes I write as a volume in liters so that you know for sure. Okay. Yes, so you just take the moles that you've calculated here and divide it by the volume. But what is this volume now? No, what is the number of milliliters? Say that again. It's not 25. No,
0 to
75 milliliters. Because you mix two solutions together and the final volume now is bigger than either one was. All right, so let's go ahead and do this. So we start with the molarity and volume of the AgNO3 to get the moles of AgNO3. So, okay, what is the volume of the AgNO3? That's right, which is 0.0500 liters. So let's call this step 1, step 2, and step 3. So here's step 1 down here. We have 0.2, we have the volume I write first, 0.0500 is 50.0. I have to keep my significant figures, okay? 50.0 liters times 0.20 moles per liter. And let's not forget what this is. This is the AgNO3. So when you multiply that out, you get 0.010. It's actually 0.01. Oh, this is 2 sig figs here. So I only keep 2 here. All right, so my second step is to use the moles of the AgNO3 to get the moles of the MgNO3 too. So what do I put in here? What goes on the bottom? I want to get rid of moles of AgNO3. Yes. Exactly. And what goes on top? I want to get what? I'm trying to get MgNO3 too. That's right. 1 mole MgNO3 2. Okay. And so I'm basically multiplying by a half. Okay. And now the third step here is to take and divide the moles by the liters. And the volume in liters here, let's not forget, it's 25.0 plus 50.0 in milliliters. So it's 0.0750 on the bottom. This is liters of solution, of the entire solution. So it's 0.0050 moles divided by 0.0750 liters. Point 0.067 molar, okay, of MgNO3. NO3, 2. Okay. There's another step. It says how many grams of AgCl is produced. I'm going to do that I'm going to give you a special problem. So I'm going to call that SpAgCl. Okay. And I'll collect it next week. Okay. So the next problem, I'm going to actually talk about this problem for a while, this next one. It's a similar kind of thing. It says that a certain amount, it gives you the amount of, and the molarity of a solution of KOH. And it says it completely neutralizes, I'm going to talk about this, 20 milliliters of an unknown concentration solution of H2SO4. All right, so what I first want to do is talk about this reaction. I might as well balance it first. How do we balance this equation? What do I have to do? What's a glaring error here? Yeah. You have two Ks here and you have only one here. So you put a 2 there. Now you have 2 Ks on each side. Okay. What about the H now? Let's balance. Oh, sulfate is balanced. You can see you have one sulfate, you have one sulfate. So we're kind of left with the hydrogens and oxygens. Let's do the hydrogens. The hydrogens, you have 2 hydrogens here, and you have 2 here as well. That's 4. So what do I have to do here? Put a 2. And now when you do that, you see that here, if we consider the SO4 as those oxygens separate, we have 2 oxygens here, and we have 2 oxygens here now. So we're balanced here. This is a balanced equation now. 1 to 2 to 2 to 1. All right. But I want to talk to you about what type of reaction this is before we actually solve this problem. Okay. So what I want to tell you is that H2SO4 is an acid. It's sulfuric acid. And KOH is what we call a base. Leave a little space. That's potassium hydroxide. We know that from earlier study. But here's the thing, and we're going to cover this next week, but I wanted to do some stoichiometry with this stuff. Acids are substances that produce H+ ions when they're dissolved in water. And we'll spend some time talking about this next week, so don't have to understand everything now. Bases produce OH- ions when dissolved in water. We call this type of reaction an acid-base neutralization. And the reason we call it that is because the H+, which is from the sulfuric acid, which is in solution, so it's aqueous, combines with the OH- from the base, KOH, to what do you think happens when those two come together? Yes, H2O. So whereas before, you had something acidic and something basic, H+ is the essence of being an acid, OH- is the essence of being a base, but when you have the two together, they combine, they cancel each other out, they make water, and we call water neutral. So that's why it's called a neutralization. So this is happening in every acid-base reaction. It's not the only thing that's happening here, because as you could see, what we have is we have an acid plus a base. You get water always. and always produces water because this is effectively always happening in an acid-base neutralization reaction. But the other thing that you get is called a salt. It's simply an ionic compound that's produced in an acid-base reaction. And we will go over this. These aspects I won't test you on next week because this is about chemical reactions. But you will have to know how to do these type of stoichiometry problems. So anyway, so that's kind of a little bit of the background of this problem. But now we can go about, actually doing the problem. Okay, and don't forget we had balanced this. This was a 2, a 1, a 2, right? Yeah, 1 to 2 to 2 to 1. Okay. So let's read this again, okay? 17.80 milliliters of a 0.344 molar solution of KOH. So we have this reactant. We are able to figure out from this, we can get the moles of the KOH. Be able to figure that out. It completely neutralizes 20 milliliters of an unknown concentration solution of H2SO4. And what you're asked to find out is what that concentration is. So what are you given here and how are you going to be able to use it? So, what you have to do is you have to use the molarity and the volume of the KOH to get the moles of KOH. Now, when you know the moles of KOH, and that many moles completely react with the acid here, what you're going to be able to figure out is how many moles of acid, how many moles of H2SO4 were in that 20 milliliters, right? So the next thing you have to do is you're going to use the stoichiometric ratio or the mole ratio of H2SO4 to KOH to get the moles of H2SO4. Once you have the moles of H2SO4, what are you going to do to get the volume of the original H2SO4 solution? To get the molarity, you're going to divide by the volume. So let me ask you, okay, so you're going to divide the moles of H2SO4 by the volume of H2SO4. Now, this is where they actually want to know what was the original concentration of the H2SO4, right? At the end of this reaction, there is no H2SO4 and there is no KOH. They've completely reacted away. And what you have is this compound and water. So the question is asking, what is the molarity of the H2SO4 solution? And the reason I'm talking about this so much, this last aspect, is because some people want to divide by 17.8 plus 20, that volume in liters. And that's not what you do here. What do you divide by here to get your answer? The volume of what solution? The H2SO4 solution. So you divide by the 20 milliliters converted to liters. Yeah. How about if you work on that? Okay, use the molarity and the volume of the KOH to get the moles of KOH. How do you do that? Remember, molarity is moles per liter. So you take moles per liter multiplied by liters, and that gives you moles. Think about it. Give you a chance to think about it. I'll come around. You have a question, ask. What do you need?
That's why, okay. My neighbor. I see a lot of people trying to get moles by dividing molarity by liters. I've seen this 5 or 6 times already. It's not very good. You have to multiply molarity by liters. Molarity is moles per liter, and our liters will cancel. So start off doing it that way. It gets actually on that one. I've done that. Please, oh, that's well done. I'm like, what am I doing? That's you're trying to find that.
So. Yeah. I mentioned this. That's the.
You get your. Remember where you got it. Molarity. I don't know. Just want to do that.
Other than you like.
I could tell it, like, I wouldn't regret it, but I couldn't try it off again, I did. And then tried out. She was not too late at night, but it's been good. Oh, that's what she did. All later. I did. Good. You're up by a factor of 10. Better. And so is one of the people. Now your thoughts multiply, right? Clarity. It's not, it's false. With, right? You can say you can cancel. I don't know. So that's the thing. You want to find polarity of the divided by the volume. There is 21 liters. Yeah.
I do.
Oh, that's
Yeah.
All right, so I'm gonna go over this problem.
So I have the KOH is what we're going to start with. This is number one. We have 17.80 milliliters. That's 0.01780 liters. Okay, stop me if you don't understand something. 0.344 moles per liter. That's what molarity means. Cross out liters and you get moles. And it's important that you keep the significant figures here. A lot of folks don't want to do that, but then you lose information. You have calculations that come later, and you know that inaccuracy or imprecision, it compounds itself as you go through these calculations. So it'll give you an answer that we say has round off error if you say rounded this to 0.006 or something. So that's the moles of what? That's the moles of the KOH. Now we use that This is number 2. You use that to get the moles of H2SO4. So we're going to put in the stoichiometric or mole ratio, 1 mole of sulfuric acid to 2 moles of KOH. So you're basically just dividing by 2. Okay, now that you have the moles, molarity of the H2SO4 is the moles of H2SO4 over the liters. This is the original H2SO4 solution. So what we want to know is what was that concentration originally? And so that's why we're dividing by that. That was the volume of the H2SO4, and it comes out to 0.153 molar. Okay, now this type of problem is one that you see quite a bit. It's a very typical problem. In fact, you're going to be doing this in lab, something like this. It's unfortunately a couple of weeks from now, October 16th or that week. And so, you know, if you look at the way this problem is written, it says 17.80 milliliters of whatever molar solution of KOH completely neutralizes 20 milliliters of an unknown concentration of H2SO4. So you have to ask yourself the question, you know, how do we know that exactly 17.80 milliliters of this solution completely reacted with the H2SO4 that was there? So does anybody know the kind of technique that we use in acid-base reactions very often to figure out an unknown concentration of the acid or base? Does anybody know? Have you ever done one of these experiments in high school, maybe? It's called a titration. How many of you have done a titration? Boy, I guess this was all during the pandemic or something. Nobody had labs. Well, you're going to do one this semester. So it's called a titration, and a titration is a process. I'm just going to tell you what it is, where one reactant of known concentration, so you know the concentration of one reactant, and in this case, it was the KOH. It had a 0.344 molar concentration, so is slowly added to another reactant, which is the H2SO4. So I'm going to write down, this was the KOH was added to the H2SO4 solution, okay? Whose concentration is unknown. Okay, and why is this done? This is done to find the concentration of the unknown solution. Or find the molarity. In our case, it's the H2SO4. So the way it's done is you have this thing. This thing is called a burette. Did you use a burette this week? Yeah, well, those of you who haven't had lab yet, maybe you've never seen one. It's this calibrated long skinny tube. And in the tube, we would have the KOH, okay? Over here, we have an Erlenmeyer flask, and in it, we have 25 milliliters of the H2SO4 solution, okay? And so basically, you drip in the KOH, add the KOH slowly, even drop-wise, which means a drop at a time, okay, to the H2SO4 solution. And you add it just until you have just reacted all the H2SO4, until the H2SO4 has just reacted. In other words, you don't add any extra. You add just the right amount to react with all the H2SO4 that's in there. So what's the question that you might want to ask here? KOH is a clear solution. H2SO4 in water is a clear solution. You add two clear solutions together, it's a clear solution. In this case, the product is clear. Products are all clear. Water is clear. So what's the question here that you should be asking? Yes. Say that again. How do you know when to stop? How do you know when all the H2SO4 has just reacted? Does anybody know the answer to that question? Yes. Sorry? It changes color, right? But I just told you that it doesn't change color, but you know it changes color if you've ever done this before. Why does it change color? Yes, you add something called an indicator. We use an indicator. Okay, and the indicator that we use is called, okay, here goes, phenolphthalein. You don't have to know that name, but phenolphthalein, you always kind of have to spit a little when you say it, if you say it right. So I try not to say it right. Phenolphthalein is a very interesting chemical. And what you do is you add a few drops of a solution of phenolphthalein, phenol, etc., to the H2SO4 at the beginning. All right, now I didn't give you copies of this because I couldn't make them in color anyway, so it wouldn't have been very informative. And plus, this is way beyond the scope of our course here, but I want to show you that phenolphthalein is what we call an acid-base indicator, and it has a different structure. All I want you to do is look at this big structure on the left and this big structure on the right, and to notice that there are differences. Okay, what you can notice right away is you have an H here that you don't have over here. And there's something going on here that's different from over here. That's all I want you to notice, that there's a difference in structure. And the structural difference causes the chemical to have a different color, because color, the chemical has to do with the colors that the chemical absorbs. And the way a chemical absorbs depends on its structure. So if it absorbs different chemicals, it will transmit different colors, it'll transmit different colors, and it'll have a different color. So the important thing to notice here is that in acid, so this is the acid form, it has an H here, and this is what it looks like in base. So what happens in your titration is you start out, you have your H2SO4, and it's clear, and that's because it's in acid. But then after you add the KOH, okay, and you go one drop further, one drop, one tiny fraction of a drop more than just reacting all the H2SO4, now all of a sudden the solution is basic because it has OH minus ions, and the thing turns pink because it's pink in the presence of base. So this is a wonderful thing, this indicator, and there's many different ones that we use for different titrations. And we'll do some of that later in the semester. Oh no, actually Chem 104, you'll do that. But anyway, well, you'll do a titration, an acid-base titration, like I said, on October 16th or that week. So I want to show you a little bit what it looks like as you're doing this. So here is your H2SO4. Your KOH is in this burette. Okay, now you have the indicator is in here. It's in the H2SO4. And you'll notice that there is no color except for my stupid pen, which it won't erase now, so. Okay, so it's colorless at the beginning, so it's clear because it's acid. So then you have KOH in here. Now you're adding some drops of KOH. You can see that right where you put the drop, right over there, see that pink color? Why is it pink? Because you just added KOH to that spot and it hasn't reacted with the acid yet. Once it reacts with the acid, it becomes clear because now you still have more acid there. You're only adding a little KOH. All that KOH reacts and you end up with a lot of the H2SO4 that hasn't reacted yet. So you'll see a little pink color and then it'll disappear. And you'll add more drops and you'll see a pink color and then it'll disappear. While this is happening, you're using up the H2SO4 a little at a time until you use the last little bit of H2SO4, and then you can tell that you've used it all up because the next fraction of a drop turns the thing pink because the KOH doesn't have any more H2SO4 to react with at this point. Okay, there's no more H2SO4 for KOH to react with. So KOH remains in solution. KOH has OH minus, that's basic. So the thing turns pink. So you could tell you're at the end point when it turns pink, okay? And we could tell if you added too much because it turns wicked, crazy dark pink. What you really want is a nice light pink, okay? So that's how this works, and that's how you tell. And when you've just added that tiny, just added, you see a slight pink color, we call it the end point, is when just enough KOH is added. And you see a slight pink with a slightly bit of extra KOH that turns it all pink. So at the end point of the titration, we know from the ratio of the moles, right? We know that, what was it? H2SO4 plus 2 KOH, that was on the left side of the equation. So right at the end point, we know that the ratio of the moles of KOH that you added to the H2SO4 that was originally there was 2 to 1. And that's how we use the moles of KOH to get the moles of H2SO4. So we have to get to the end point. And at this with this particular problem, it was when 17.80 milliliters of the KOH was added. Okay, so that's a titration. So that's a very typical type of problem that you have to do. And so maybe you'll know when you get there. All right, let's see. Oh, hold on. So this is a very straightforward problem. Let's see how much time I have. Oh, man. All right, let's just do this problem. The reaction is written here. Okay, it's already balanced. So this is a very straightforward problem of figuring out, you have HCl of unknown concentration. So you start with 30 milliliters of the unknown HCl. You add an indicator. And here it tells you the concentration of the NaOH and the volume of the NaOH. So you're going to use the molarity and volume of NaOH to get the moles of NaOH. Okay, when you're done with that, you're going to get the moles of HCl from that. And finally, you'll calculate the molarity of the HCl. So why don't we just do this problem? It's activity for number 1. So you have it written down already. If you finish this one fast, then the next problem is a special problem. You could work on that.
So what volume you use to get the moles of KOH? know the molarity, right? It's written down there. Sorry, NaOH. Right, that, it's a 16.37 milliliters converted to liters. That's the volume of the NaOH. So that's what you multiply by the molarity. There's two volumes of this problem, and that's one of the things that people are wrong.
And this is a problem where you actually have 4 significant figures. So you have to keep them. So the moles of NaOH, you have to keep the 4 sig figs and do that. How do you get the moles of HCl though? Is that going to be hard here? This is the balanced chemical equation, is 1s everywhere. So what is the moles of HCl going to be here? Speak up, speak up. Of the NaOH, right, because you have a 1-to-1 mole ratio. So the moles HCl is just, 2.005 times 10 to the minus 3. You could do it this way. Start with the moles of NaOH and put it on the bottom, 1 mole of NaOH on the bottom, 1 mole of HCl on the top. But you're really just multiplying by 1, so it's the same. So now all you have to do is get the molarity. So how do you get the molarity now? What's the definition of molarity? Say it loud. That's right, moles over liters. So, it's the moles of the HCl over the liters of the HCl. Okay, so I write that because there's 2 different volumes in this problem. And the HCl, if you look at the information that was given, it's 30 milliliters of an unknown HCl solution. So what's that in liters? 30 milliliters. I didn't hear the answer, but that's the answer. Wait. No, trying to erase that. Can't stand it. Okay, so it's 2.005 times 10 to the negative 3 moles over 0.0300 liters. And that comes out to 0.0668 molar. And that's how you do that problem. If you look at the next problem, it's a little different because the known concentration is the acid. So, so this would have the acid in the burette, slowly adding to the solution of the base, calcium hydroxide. So this one would actually go from pink to clear. You don't need to know those details now, though. Just treat it as a stoichiometry problem. So this is a special problem. I'm not going to go over that. All right. So I'm going to start something new, even though we only have about 15 minutes. But I'm going to start talking about a different, somewhat, a little bit, another aspect of stoichiometry. So I want to say that up until now, you've been given the amount of really just one of the reactants. So for example, in these solution stoichiometry problems, you were only able to figure out the moles of one of the reactants. Like in the last example, it was the NaOH, and that led you to figure other things out. In the previous example, it was the KOH. In different examples that we've done, you've only been given information to determine the amount of moles of just one of the two reactants. It's always assumed that the correct amount of the other reactant reacts with it, right? So you've only been told the amount of just one of the reactants, and we've assumed that. So the thing is, what if most of the time when you run a reaction, you have a certain amount of one reactant and a certain amount of the other reactant. They're not necessarily there in the right ratio to react. So we know that these stoichiometric coefficients, they give the ratio of moles of reactants to one another. But what if the reactants aren't present in that ratio? You know, instead of a 1-to-2 ratio, what if they're present in a 1-to-3 ratio? So what's going to happen in that case? So what if what's present in the flask, right, in the reaction flask, is not in the proper or correct stoichiometric or mole ratio of reactants? Okay, so what's going to happen in that case? So reactants in a real reaction in the lab are often present in amounts that differ from the correct stoichiometric ratio, and there are various reasons for this. Okay, but what it means is if you don't have the correct mole ratio in the flask, you know, what happens? Well, of course, they're going to react. But when the reaction is done, one of them will be left over, right? Because they weren't present in the right ratio. One of them will get used up and one of them will get left over. Okay, so what happens is one reactant will get used up. And the other will be left over. Okay. So the one that gets used up is the one we say it was in limited supply. And we call it the limiting reactant or the limiting reagent. And the one that's left over, we say that it is in excess. And we use the excess for that, okay? So why would you run a reaction where you don't have the stoichiometric ratio of reactants in the flask? Why would you ever run a reaction that way? And there's many reasons for that. I'm just going to give you a couple of them. You know, chemicals do not all cost the same amount, okay? You could have a situation where one reactant is very cheap and the other is really expensive. I remember when I was in grad school, I had to do a reaction with a reagent that cost $1,000 for a milliliter. And so, yeah, I was really nervous about that reaction. But what I did was I used a milliliter of my expensive reactant and I used a lot of extra of the other reactant to make sure that all my expensive reaction got used. Okay, so one reactant is cheap, another expensive. You would use extra of the cheap reactant. to make sure all the expensive one was used up with no waste. You don't want there to be leftover expensive what's that? How do you know how much more? Oh, I don't know. Maybe you put 20% more or something. I don't know. Yeah, I don't know the answer to that. Maybe it doesn't even matter that much. I mean, you don't want to drive the equilibrium the other way, but there's a lot of things in that question that are deeper than what we talk about here. Another reason would be, let's say one reactant is not pure. You know, there's a lot of chemicals on the shelf that have been there a while. And if you know that one tends to break down, you know, you might put extra of it to make sure that you have enough of the chemical that you need for the reaction. If it's not pure, you would use extra to make sure you have enough. And there's a lot of other reasons as well, which have to do with the ease of working up the reaction when you're done. What, you know, if you have something that's very hard to separate from the product, you wouldn't want to put extra of that in. So there's all kinds of different considerations that you come across in the lab. But the fact is that there are many considerations, and there are many times when you do not have the stoichiometric ratio of reactants in that flask. So we need to know how to deal with situations in reactions where the reactants are not present in the stoichiometric ratio. Okay. And what I'm going to do, I'm going to spend a little time talking about a situation that you could run into in everyday life where you have something similar. So here's a story. I don't know if one day maybe your child or your kid brother or sister comes home and says, there's a bake sale at school. I signed you up to bring cake. You know, so your 5-year-old sister is saying, you know, you have to bring cake tomorrow. You have to bring cakes tomorrow. And let's say it's 9 o'clock at night or something. Or maybe let's make it 8 because it's really 9 is kind of late for baking. But so, you know, you don't have time to go to the store. You don't want to go to the store. And you just want to get this over with. So you look in the cabinet and in the fridge. And, you know, you look up your recipe. You see that you have lots of sugar. You have vanilla, all that stuff, blah, blah, blah. And in the fridge, you have 1 dozen eggs. And you measured it out. You have 9 cups of flour. Okay. So you have 9 cups of flour and you have 1 dozen eggs. And let's say that you find a cake, your favorite cake recipe calls for 3 cups of flour and 2 eggs. And everything else you have plenty of. So you're thinking, okay, how many cakes can I make if I have 9 cups of flour? So what's the answer to that? What's the number of cakes that you can make? 3 cakes. It's obvious that it's 3 cakes. How did you figure that out? Well, there's actually more eggs than cups of flour. Ah, why is it scarce? Because you need more, right? You need, you'll run out of the flour first. So let's consider this as a sort of a chemical reaction in a way. 3 cups of flour plus 2 eggs gives you 1 cake. I keep wanting to shake the pen like we used to with the ink, but goes to 1 cake. Okay, so that's like our chemical reaction that's representing how to make this cake. Okay, and you can use these numbers sort of like stoichiometric or it's a recipe ratio, if you will. So if you have 9 cups of flour, you can use this. You could say, okay, to get one cake, it's 3 cups of flour. So I have my product to reactant ratio, and that would be 3 cakes. You didn't have to do that. You could do that in your head. But 12 eggs, 1 cake has 2 eggs, that gives you 6 cakes. So, you could say, if you have 12 eggs, you can make 6 cakes. Well, but if you have 9 cups of flour, you could only make 3 cakes. So how many cakes are you going to be able to make? 3 or 6? It's pretty silly, right? This is what's going to happen, is you're going to make 3 cakes. Well, it's the same way when we do limiting reactant problems, which I'll show you next time. Whichever reactant gives you the smaller amount of product must be the limiting reactant. So this tells you that the flour is the limiting reactant because you get less product. Okay, well, I'm done. And I think that probably we will not have limiting reactants on the exam because we really didn't get to it. So don't forget that I have lists of topics. I have the topics for chapters 1, 2, 3, and what we've done in chapter 4. I indicated on there that we have done limiting reactants. We'll have done it by today, but we haven't. So that will not be on the exam. So we can ignore those problems on the review sheet. It's a couple like that. So problems 16 and 17, you won't have to do. All right. The one that has 4 bunch of pages says review problems for exam 1. No, you don't hand that in. That's for you. I'm going to post the solutions at some point. But I'm saying that 16 and 17 shouldn't be on there because we didn't get to that topic. What are you shooting about?
I did it. It's this special problem that's not due today, as and I need to copy it down on paper because I can't turn it over.
4B?
Yeah.
No, it's not due today. Yeah, I just have to walk there, so it'll take me a little longer.
I got a quick question. Like the meetings you set up for like the board exam stuff, do you want us to finish this before we head?
No. No, I want you to, I want you to bring your questions. Yeah, I don't actually lecture there. We just go over problems. Or questions from quizzes, anything like that. What are you asking me?
Oh, it's the headline programs of
Oh.
UCL's.
Okay, that's what you're finding out. Okay, let me write that down. Okay. You have your name on this? So why it's so difficult.
Besides special problems from us.
Nope. Nope.